Good morning, everyone. Today I will solve your first online assignment. So let's get started. So that's the first question. Two cylindrical resistors are identical in everywhere, except that the radius of resistor 1 is greater than the radius of resistor 2, R1 greater than R2. Which of the following statement is correct? So, resistance of resistance R1 is equal to the resistance of resistor R2. The resistance of resistor 1 is less than resistor 2. It's not possible to compare the resistance, or the resistance of resistor 1 is greater than the resistance of resistor 2. So if you have a cylindrical resistor, that's something like that. Okay, so we have R1 here. They are identical, so they have basically same length and they have the same material, so they have the same electrical resistivity. Okay, and the resistor 2, so R1 greater than R2. Okay, so R1 greater than R2, something like that. They should have the same length, sorry. So that's L, that's rho. So basically, if I take R1 is equal to what? Rho L over the area. What is the area? Pi R1 squared. And if I take R2 is equal to rho L over pi R2 squared. So if R1 greater than R2, what we did use? Resistance capital R1 is smaller than resistance R2. So that's the right answer. As simple as that. Question 2. Kirchhoff loop rule states that the algebraic sum of potential difference cross around closed loop must equal to 0. Okay, that's loop rule. That's loop potential rule that we know. This rule is a consequence of which of the following? Conservation of charge. Conservation of charge, no, that's the junction rule. Okay, conservation of charge is junction rule. Ohm's law, of course not. Newton's law, that's not this. Conservation of charge, that's a conservation of, energy. Okay? What is the energy? QV. We have loop rule talk about potential. Okay, so that's the conservation of energy. If you have delta U, if you have delta V equals 0, what did you use? Did you use that delta U is equal to 0? That's a conservation of energy. Okay. Next question. It's about magnetic force. The figure below shows 3 situations in which an electron, that's very important, is in bold, moves at velocity v through a uniform magnetic field B and experience a magnetic force Fb. What is Fb? QV cross P. Determine which situations are physically reasonable for the orientation of the vector. Okay, so first one, A, is this reasonable? Of course, no, directly. Why is that? FB is perpendicular to V and FB is perpendicular to B. That's a consequence of this. The force is perpendicular to both velocity and magnetic field. So this is wrong. FB is not perpendicular to B here. And FB is not perpendicular to B here. So that's wrong also. So let's see this one. That's reasonable because FB is perpendicular to V and B. Now, let's think about it. If we have an electron is a negative charge. Okay? You do V cross B is out of the page, so where should be the force? Into the page. So here the force shown is out of the page, so this is wrong too. So none of them is true. None of them is true. Next question regarding to circuit. A voltmeter is connected across terminal of a battery while the current is varied. The figure below shows a graph of voltmeter reading V as function of the current through I, current I, through the battery. The EMF and internal resistance of the battery are, okay, so in EMF and internal resistance, what it means? Battery, non-ideal, because it has internal resistance, okay? How we draw a battery? That's negative, positive, but there is internal resistance R, that's the battery. Okay, that's the battery, that's the negative pole, that's the positive terminal. Okay, and we have a current flowing in this direction. And we measure, so this is basically connected to a circuit, okay? And so there is a current source here, there is something that brings current. Probably is connected, let's say, connected to an external resistor, for example. It's not necessarily to draw that. And the two terminals are connected to a voltmeter to measure volt. Okay. What is the relation between V and I? We learned that. V is difference in potential, actually. It's delta V. What is delta V? Across the terminal of the battery. So this is an EMF. So it's E minus Ri. Okay? So that's delta V. E minus Ri. When E minus Ri, when current I is equal to 0, delta V is equal to what? E. So that's E. That's the EMF. It could be this, it could be this, or it could be this. These two are wrong. And what is the internal resistor? So that's basically the negative of the slope. That's the slope. What is the slope? Slope is minus R. So let's calculate the slope, or absolute value of the slope. What's that? Delta V over delta I. What is it? 0.10, so that's 10 volt, over I, 0.4, so that's, so I take the point 0.10 and the point 4.0, okay? So over 4, this is 2.5 ohm. That's the internal resistor, 2.5, so that's the correct answer. Next question is about when you see B and E, that's a Lorentz force, right? Okay. All right. So figure show for direction for the velocity vector V, okay, of a positively charged particle. So we have positive charge and different direction of V. Particle can move in direction 1, 2, 3, and 4. Moving through a uniform magnetic field, B directed out of the page, so B is out of the page, and a uniform electric E directed to the left. The direction 1, 2, 3, 4 can be ranked according to the magnitude of the net force on the particle as follows. So you need to rank them. Okay. So let's see. Let's take the first one. V cross B, first situation. V like that, B like this. Where is V cross B? It's upward, right? V cross B is upward. That's V cross B. And E is like this. Okay? But what is, by the way, the Lorentz force? That's the charge Q, V cross B plus E. So what I need to know the magnitude. I need the magnitude of this vector. So V cross B plus E, you will get something like this. That's the force, F1. Let's take second situation, or third situation, that's similar. Third situation, what we have? We have V in this direction, B is out of the page. Where is V cross B? Downward, right? It isn't. V cross B is downward. E is to the left. Where is the vector? F1 is like that. See now, second one, V is upward, B out of the page. Where is V cross B? To the right, and E is to the left. Okay? What about the other one, the last case, 4? V is downward, B out of the page. Where is V cross B? To the left, and E is to the left. Okay, so let's take this situation. V cross B and E, they will add up, right? So the force, definitively, since the charge is positive, the force is toward the left. Actually, we are adding V cross B plus E. That's two vectors, V cross B and E. We are adding them. What is the magnitude of this vector? The highest magnitude of this vector when these two vectors are in the same direction. That's the greatest one. That's the greatest magnitude. Where is the lowest magnitude? The lowest magnitude, that's when the two vectors are opposite to each other. Okay? So you need to subtract them actually. So that's the lowest one. What about 1 and 3? Well, 1 and 3, V cross B, we have the same velocity, we have the same magnitude of B, same magnitude of E. We are adding them, right? We are adding them. They are both perpendicular to each other, V cross B and E, in situation 1 and 3. Since we have the same value for V and B, we will have the same value for F1 and F3. F1 is equal to F3 actually. Okay? So we have 1 equal 3 or 3 equal 1, the same thing. That's the answer of this question. Next question. The current in a wire vary with time t according to the relation. So we have function of current. Current vary with time. 134 minus 3 t squared, of course in ampere. So current is expressed in ampere and t in second. Fine. How many coulombs of charge pass a cross section of the wire in the time interval between 0 and 3 seconds? Okay, so we give us the current, we calculate the charge. What is the relation between current of charge? Well, current is equal, the charge is equal current times time, but this is when the current is uniform. Here we have current changing with time. Okay? What is the true definition of current? That's dq over dt. That's derivative of charge with time. So what is the charge? That's the integral of the q, which is the integral of I of t dt. Of course, from 0 to 3 seconds. So all what we need to do is to integrate this expression from 0 to 3 seconds. Okay? So let's integrate that. 134 minus 3 t squared dt. Simple math. 134t minus 3 t cubed over 3. Isn't it? This taken from 0 to 3. Okay? 3 will cancel out with that. So we have 134 times 3 minus 3 cubed. You do the calculation, you found 375 coulomb. And you write it over here, 375. And you don't need to add the unit. Even if you add it, it's fine, but it's better to not add it in this kind of question. It's just a numerical answer. Next question. Circuit. That's a simple circuit. In a figure below, R1 equal 48 ohm, R2 equal 51 ohm, and the ideal battery has an EMF E 12 volt. What is the magnitude of the current I1 through resistance R2? I1 is drawn here, so let's calculate it. Okay. All right. So let's start. What we do, we need to simplify the circuit. Do we have resistance in series, in parallel? R2, the 3 R2 are in parallel They are in parallel. So what we do, that's the circuit, right? That's R1, and this is the equivalent circuit, the equivalent resistance of the three resistors that are identical. That's R2 over 3. Okay, that's the EMF. Good. So what we can do, you ask yourself what I can calculate. We can calculate the current, the total current. What's that? E over R1 plus R2 over 3. I don't prefer to calculate numbers here. You can do it if you want. What we do next? Next, I can calculate the potential here. V, okay, what's V? That's R2 over 3 times the current. You do that here, you get E R2 over 3R1 plus R2. Okay. What I do with this voltage is the voltage between this point and this point. So what is the current I1 now? Straightforward, I1 is equal to what? V over R2. Simply, that's the potential. V is the potential cross R2. So what is the current I1? V over R2. So you do that, you get E over 3R1 plus R2. And you calculate that. E, 12 volt, 348 plus R2, 51. You calculate that, you get 0.0615 ampere. Which one is closer to that? That's the answer, if we round it. Done. Next question, we still stay in circuit. In the figure below, all batteries are ideal. We have 3 batteries, 8 volt, 4 volt, and E, we don't know it. If the current through the 8 volt battery, I, the current I, where is it? This one. If this current is equal to 1.82 ampere, find the current through a 6 ohm resistor, current here. Okay, so we have this current I coming here. Here there is junction, but we don't know the direction of this current in the 6 ohm resistor. We don't know it. What we do if we don't know? We assume. We assume a direction like that. Let's call it I1, simply. If I1 is positive, it means I choose the correct direction. If I1 is negative, it means that I have the opposite direction, and that's it. But I will find the value. All what I need is the value. Good. So let's do that. So now we need to choose a loop. So it's better to choose the loop when we have just one unknown as the exterior loop of the circuit. So let's do it and write a loop rule. What we have? 8. The current flowing here in this direction minus the resistor 1, resistance is 1, times the current 1.82 plus 4 minus again 3 times 1.82, and here also minus 6I1 equals 0. Done. What we have, if we arrange this, 12 minus 1 minus 3 minus 4, 1.82 equals 6I1. So what is I1? 12 minus 4, 1.82 over 6. You use your calculator, you get 0.786, maybe something else. So what is the closest answer, rounded answer? This one. That's the true answer. 0.79 ampere. Done. Now, next question. Magnetic field, so this is magnetic force. A positive charge Q equal 0.1 microcoulomb moves with velocity v, so v is given, along ijk direction in meter per second, it's fine. In a region of uniform magnetic field, B equal 4I plus AJ minus 12K Tesla. What is the X component of the force? Okay, I don't need to calculate the whole force. I need just to calculate the X component of the magnetic force. What is the magnetic force? Q V cross B. What we need to do? To calculate V cross B. But not exactly. I need just the X component. What it means X component? Fx along what? Along I direction. So I need to calculate V cross B and take just the I direction. What is the component of V cross B along I direction? So let's write V cross B. V cross B is 8I minus 16J plus 4K cross B. B is 4I plus 8J minus 12K. Okay, I need to calculate the I component. Where is the I? It comes from the cross product J cross K. That's I. Okay. So what I have? Minus 16J cross minus 12K. So minus with minus is plus, so we have 16 times 12 J cross K. That's what I need. I don't need other components. And what I have? 4K cross 8J. So plus 4 times 8 K cross J. Now, so you don't need to calculate the whole force. If you did that, you wasted time for nothing. J cross K, what is it? I. K cross J, that's minus I. That's all what you need to know. Now, what is the Fx? The charge, 0.1 microcoulomb. Let's keep it like that, because you will see here the forces are in micronewton. So let's use this micron. Times 16 times 12, positive, the x direction. This is a negative x direction, so minus 4 times 8. Good. When you do that, what you will obtain? 16 microcoulomb plus 16. That's the right answer. Next question, RC circuit. So we are given the EMF, the resistor, and the capacitance. All right. First, the switch S is closed on point A. So what we have? We have charging until the voltage cross the capacitor equal to that cross the resistor. We have this kind of circuit. First step, RC, that's by the way point A, that's the EMF E. So we continue this charging until the voltage cross capacitor equal to voltage cross resistor. So VR or delta VR equal delta VC. Okay, voltage cross resistor, that's R times current. The voltage cross the capacitor, that's Q over C. All right, Q equal CE1 minus exponential minus T over tau, and I equal E over R exponential minus T over tau. You plug this here, what you get? E exponential minus T over tau equal E1 minus exponential minus T over tau. You cancel out the EMF. And what you did use? You did use that exponential minus T over tau is equal to what? Half. No need to go further. You will see that no need to go further. There is no need to calculate the time. If you did that, you wasted time for nothing. Just after that, the switch is closed on point B. So the second situation, we close the switch on point B at this time. At this time, we close the switch on point B. So we have discharging now. C, R. The experiment ends when the current decreases by 75%. Question, what is the final charge on capacitor? So what we can say here, what is the charge? That's the initial charge exponential minus t over tau. And what is the current? That's the initial current exponential minus t over tau. Okay? So what they say here, the current decreases by 75%. So it means the current now, if it decreases by 75%, what is it now? 25% from its initial value. Okay? Equal I naught exponential minus t over tau. What I can deduce from here, exponential minus t over tau equal to what? 0.25. And the question is, what is the final charge? It means the final charge, what is it? I can get it from here. The final charge is the initial charge times 0.25. Good. The thing here, what is the initial charge here? When the switch is moved from A to B, what is the initial charge? Well, the initial charge of step 2 is equal to the final charge of step 1. So what is the final charge of step 1? What is it? I can replace it here. CE 1 minus what? 0.5. So this is CE over 2. Okay? And this is equal to what? Is equal to what exactly? Q naught. So we use this here. What we get, what is the final charge? CE over 2 times 0.25. So it means CE over 8. What is C? 15. E? 12 volt. And what you get, you do that, you will get 22.5 microcoulomb. Not too difficult, just two-step problem. That's the right answer. Next question on magnetic field now again. So we solved this kind of question many times. That's the right answer. Next question on magnetic field now again. A proton moves in a uniform magnetic field, goes through a 90-degree turn, so it moves like this, that's proton, it moves like this and it goes through a 90-degree turn. So you see here a 90-degree turn, right? So it helps you further, it tells you that this is a quarter of a circle, not a circle, not a complete circle, a quarter of a circle. And then it exceeds the field region. So it enter here, it do quarter circle, and it exit here. If the proton spend 235 nanoseconds in this region, find the magnitude of magnetic field. Okay. So he gave us time t. What is this time t? You remember the time that we have when we have a charge inside the magnetic field. What we have? Which time we have? We have just a period capital T, right? So what is this time compared to the period? The period t is for the whole circle. Here we have a quarter of circle. So what's that? Quarter of the period. And what is the period? 2 pi m over qb. Okay, you put that here, what you get? Pi m over 2 qb. And from here you deduce b. Pi m over 2 qt. Right? So let's write it. Pi 1.67 10 to power minus 27, that's the mass of a proton. 2, charge of proton 1.6 10 to power minus 19, and the time 235 nanosecond 10 to power minus 9. You do that, you will get exactly 6.97 10 to power minus 2 Tesla, that's B. So which value is close to that? This. Next question, still with magnetic field. This time we have an electron instead of proton. So mass is given. The electron has a velocity v equal 17I plus 35J kilometer per second. That's very important. 10 to power 3 meter per second. Convert from now. Okay, to not forget. Good. B is equal 72 micro Tesla, so 72 10 to power minus 6 Tesla along I. Good. So we have B, we have V. Calculate the radius of the path taken by the electron. Okay, so we have a charge. Let me ask you this question. You have a particle inside the magnetic field. Which kind of path this particle can move? In which direction? In which path? There are three paths. If the velocity parallel to B, it go in linear path. If velocity perpendicular to B, is a circular path. If velocity is not perpendicular to B, okay, and not parallel to B, you have a helical path. So which path we have here? Well, let's draw simple things. Let's have X, Y axis, okay? Where is B? Where is B? B along X axis. Where is B? B 1735, so something 1734. Okay, so something like that, maybe, right? So which path we have? Helical path. Very important, because the radius, the expression of a radius depends on that. Which path? The radius of a circular path is not exactly equal to the radius of a helical path. They are different. So here what we have V perpendicular, V parallel, okay? What is the radius? So the expression of a radius we know, mv over qb. You need to remember that. But which V? V that is perpendicular to B. That's the expression we calculated where? When V it was perpendicular to B. So this is V perpendicular. Now, where is V perpendicular? Let's look at it. We have V equal 17I plus 34J 10 to power 3 meter per second. And B is equal to what? 72 Tesla, 72 along I, 10 to power minus 6 Tesla. That's the unit. Okay, so B is along I, and V is along I and J. So that's where is V parallel? That's V parallel. That's along I. Where is V perpendicular? Is the component along J. So it's 34. So what you do? What is the mass? 9.11, 10 to power minus 31. What is the velocity? 34, 10 to power 3, divided by 1.6, 10 to power minus 19. And B, what is it? 72, 10 to power minus 6. 2.6887, 10 to power minus 3 meter. All right, that's what my calculator give me. So what is it? That's in millimeter, okay, millimeter. So how we can write it? 2.6887 millimeter. When I round it, 2.69 millimeter. So that's the true answer. Okay, next question. A long wire carrying 7.4 ampere current makes two 90-degree bands. So that's the first 90-degree band, the second 90-degree band, as shown in figure A. As shown in figure, a uniform field, 0.23 Tesla magnetic field, is confined to a limited place, limited space region. So 60 by 60 centimeter square. In this square, we have a magnetic field, uniform magnetic field. What is the magnitude of the magnetic force on the wire? Okay, so we need to calculate the force on the wire. What is the force on the wire? I, L cross B. Okay? We have three portions. Inside the magnetic field region, we have three portions. That's the first portion. Let's call it L1. That's the second portion. Let's call it L2. And that's the third portion. Let's call it L3. Let's see direction of the force. So L1 cross B. Where is the force? Upward, F1. L2 cross B, where is the force? To the right, F2. L3 cross B, where is the force? Upward. So we have, if I call this X and Y, we have X component and Y component of the force. What is the X component? Fx, that's F2, which equal to I L2 times B sine 90 degree. So 1. I L2 times B. L2 is given 30 centimeter. Good. What is Fy? F1 plus F3. Okay, they are in the same direction, of course. So I L1 times B plus I L3 times B. All right, what is L1? I don't know. What is L3? I don't know. But if you can see here, you have IB, that's common factor. L1 plus L3. What is L1 plus L3? I know L1 plus L3. That's L1 plus L3. Okay? So I know the forces. Now I need to calculate the magnitude. Square root Fx squared plus Fy squared. So you put that inside the square root, you get IB, common factor, square root of L1 plus L3 squared plus L2 squared. Okay, so let's put numbers. Current 7.4, magnetic field 0.32, square root L1 plus L3, that's 60 centimeters, 0.6 meter. L2, 0.3 meter square. You do that, you calculate, and you found 1.417, sorry, there is one here, Newton. Which one is close? This one, right? 1.142 Newton. Yeah, we can round it to that. Good. So that's my answer. Last question. That's a complex RC circuit, but those who follow the video that I send you about RC circuit, you will find it easy. All right. So let's see. At t equals 0, the switch is closed and the capacitor is charging. So we close the switch. Good. So we have this circuit. If the resistance R1 equal 2 kilo ohm, R2 equal 802 ohm, calculate the current in milliampere through the capacitor just after the switch is closed. Write a numerical value without unit. Current in milliampere, you should be careful. Okay? Okay, fine. So let's calculate that. At t equals 0, I need to calculate the current through the capacitor. So this current. What is this current? All right. So at t equals 0, what we said? The capacitor behave as what? So at t equals 0, what we have? The voltage across the capacitor is 0. The charge is 0, that's an uncharged capacitor, and the voltage across the capacitor is 0. Okay, what it means? It means always capacitor became like a wire. So let's draw a circuit. So let's draw the equivalent circuit. Say like this. R1, R2, R1, and we draw something like that, a wire. All right, what is the current here? What we do? Well, you need to think about it. Here, R2, I can remove it. Why is that? Look, if there is a current going from battery, so there are two explanations. If there is a current coming from battery, where the current will go? The current will go through the wire. There is no resistance here, so he will not go through R2. The second approach, you have which resistance here? Zero resistance. And you have R2. Okay? So these two resistances are in parallel. Calculate the equivalent resistance and you will find that it is equal to zero, the equivalent resistor. So my circuit is simply R1, another R1 here, and E. So some of you were complaining because they say we get a close value of current closer to the real value. Yeah, because you included R2. You don't have to include R2. If you don't include R2, you get the right current. I will explain you. So what is this current? E over R1 and R1, they are in series. So this is 2R1. Those who included R2, what is the current? E over 2R1 plus R2. You will get a value closer to this one, but not the correct one. So your answer is wrong. Okay? So if you do that, what you get I equal 5 milliampere. So 5 10 to the power minus 3 ampere, you will get 5 10 to the power minus 3 ampere. And you need to remember here that we ask you to calculate the current in milliampere. Okay, so you write just 5 here. Okay, that's the last question that we solve. Thank you for watching.